think I've lost track, but I think this is lab 7 or 8. I'll have it numbered when I post the video. This is going to be a pH lab. Let's see, survivorship curves, you're getting some of those in, wrap those up, you're still working. Then you have the transport lab, that one's pretty easy. You're just answering those questions on the data sheet. Send me an email if you have any issues with them, but that one's pretty straightforward. No graphs or figures to make, just answering the questions. And what we'll do with this one, this is a pH lab. We'll give you a little background real quick, and then we've got like 3 procedures we're doing in this lab. It'll be similar to the transport lab. You're basically just answering questions on the worksheet. No figures to do. In fact, I'm doing most of the hard stuff for you, so it'll be a piece of cake. Another 5-point lab. You notice the 10 pointers are the bigger ones, like the survivorship curves where you got to crunch a few numbers. This one won't be too bad. First of all, pH. pH is really a characteristic of aqueous solutions. These are solutions that have water as the solvent. pH is a measure of the hydrogen ion concentration in solution. Again, hydrogen ions. Hydrogen atom's lost an electron, so it has a charge. pH is important because it impacts how other chemical reactions will occur. We mentioned it a little bit with the freshwater ecology lab. The pH of the water can have an impact on how toxic other chemicals in the water can be. pH also affects the characteristics of enzymes and other proteins, and limits how well they'll work in a given environment. So what we're measuring with pH is a hydrogen ion concentration. Now, typically you measure the hydrogen ion concentrations in moles. So chemical units, number of molecules per liter, ions per liter. But what they do with pH to make it a little simpler, since working with molar concentrations, the numbers are really big or really small. We've taken the molar concentration and actually take the negative logarithm of the molar concentration of hydrogen ions, and they come up with something called the pH scale, which many of you are probably familiar with the pH scale. It runs from 0 to 14. So what they've done is they take the concentration of hydrogen ions, they take the negative logarithm, and that's how they get this number, which is simple to work with, 0 through 14. Of course, like a number line, there's every point in between, so it's kind of an infinite number of points. You could have 5.099999, for example. But it makes it much simpler to work with than just the molar concentration. And a couple things to note, because we use this pH scale a lot. If you have a swimming pool, you might have little test strips you stick in there to measure the pH. It ensures how well your chlorine's working, condition the water. If you have an aquarium, you measure the pH, constantly to make sure it's the right pH for the species of fish you're keeping. And a few points I'll just mention on this scale briefly. 7, the midpoint. This is referred to as a neutral pH. This is the pH of pure water. If you took distilled water, measured its pH, if it's good distilled water, it should have a pH of 7. Actually, what happens, why do you have hydrogen ions in pure water anyway that's been distilled? Remember, water has an oxygen covalently bound to 2 hydrogens. Some of these water molecules, one of the covalent bonds here will spontaneously break. And remember, that covalent bond is a pair of electrons being shared, but the electrons stay with the oxygen-hydrogen part. The hydrogen that's released is missing its electrons, so it is a hydrogen ion. This piece here is also ionic. This is called a hydroxide ion. It will have a negative charge. So if you take water, some of those water molecules, depending on the temperature, will spontaneously break. Every time a water molecule breaks, you'll have the same number of hydrogen ions produced as hydroxide ions. That's kind of what a neutral pH means. It would measure as a pH of 7, and it basically means the hydroxide ion concentration, the OH, is equal to the hydrogen ion concentration. The only point on the scale where that's true is at a pH of 7. And again, because if you start off with water and you randomly break some number of water molecules, you're going to have a one-to-one relationship or correspondence between the hydrogen ions and hydroxide ions. That's pH of 7. Now, any pH value above 7, you'll usually see the term base So 7.0001 is above 7. That's considered a basic solution. So any number above 7, the neutral pH is exactly 7, is a base. Any pH value below 7, that's what we refer to as an acid. 6.99999 is below 7, it's acid. Now, I'm not going to go into the details, but this is a log scale. Every time you change the pH, let's say you go from pH of 5 to pH of 4, that's actually a 10-fold increase in the hydrogen ion concentration. It's not a 1 increase, it's 10-fold. It's that log scale compresses your scale a little bit, so the pH scale we use isn't really long. So these are acids. Another way to think of acids and bases, an acid, as you go from 7 down to 0, the concentration of hydrogen ions is increasing. So a pH of 0, it's a little backwards, has a much higher hydrogen ion concentration than a pH of 1. So it's a little backwards, that's that negative logarithm. You may confuse it once or twice, everybody does. So as you get smaller in pH value, the hydrogen ion concentration is increasing as the number gets smaller. It's a little backwards. Another way to look at it, an acid solution, the concentration of the hydrogen ions is going to be greater than the concentration of those hydroxide ions. It's just sort of the opposite when you look at a base. As you get more and more basic, where the pH value gets higher and higher, the hydrogen ion concentration is dropping, getting lower and lower. And also, one way to look at it, the hydroxide ion concentration is going to be greater than the hydrogen ion concentration as the pH value increases from 7 to say 14. So we kind of separate it into 3 clumps, especially in this lab. You have acid, base, you got neutral. Now what we're going to do in this lab, we're just going to, pretty simple procedures. We're going to use a couple different techniques to determine hydrogen ion concentration. Some of these are somewhat qualitative. Same thing you'd use, with your color charts on aquariums or swimming pools. You kind of compare color changes in reagents to get an estimate of the pH. It's not going to be spot on. The last thing we'll do is a titration, which is spot on. That's a powerful way to measure hydrogen ion concentration. So we're going to go through this lab procedure. I will post this on the Blackboard site in the folder for lab. I think it's number 7. We basically have, 4 procedures on this lab sheet. So I'll just kind of do a short video as I go through each one, just to show you what we did. Then I will post these blank data sheets, one for procedure 1, one for procedure 2. Procedure 3 and 4 are kind of combined. I'll fill these out for you, so all you'll be doing is answering a few questions. It's not going to be that big a deal. It'll be a pretty short lab for you. All right, let me get on with the first procedure, which will be determining the pH using pH paper and litmus paper. This is much like the test strips used in pools or aquariums where you stick it in and compare it to a color chart. That's pretty much all we're doing. We're going to get a handful of just common solutions, and we'll just measure their pH using pH paper and litmus paper. We're going to check vinegar, orange juice, milk, some soft drinks, and then a couple of known solutions, 0.1 molar concentration of hydrochloric acid and a 0.1 molar concentration of sodium hydroxide. That is the first data sheet we'll do. That is procedure number 1. I'll be collecting the data on this, and I'll kind of show you the results and then write it down on here for you. Take care. All right. We will work on procedure 1. Let's see if I can get everything so we can see everything. I think so. I got that intact. All right. So this will be procedure 1. We'll work on this one first. What you've got here on the left-hand side is the substance. We've got vinegar, orange juice, milk, some kind of soft drink, looks like Sprite or something, 0.1 molar hydrochloric acid, 0.1 molar sodium hydroxide. This is pH paper. It's got chemicals in it that will change color depending on the pH. So what we'll do is we'll put 1 drop of these substances on this paper. It'll change color. We'll compare the color to this color scale.
and it'll give us an approximate pH, much like a pool test kit. The other thing we'll do is really crude. This is litmus paper. It's hardly used for anything anymore. This is really, really crude. What you've got are two types of litmus paper. You've got blue litmus paper, which surprisingly is blue, and you've got red litmus paper, which, as you might have guessed, is more or less reddish, pinkish. These simply change two colors. If the solution is acidic, it'll turn red or stay red. If it's basic, it'll stay blue or turn blue, and that's it. So all litmus paper tells you is it's an acid or it's a base. Doesn't tell you the pH. If it's an acid, it could be anything below 7. You have no idea what. So it's pretty crude. Just tells you you've got an acidic or basic solution. So for the pH paper, we'll put our color here. So I'll take a little vinegar, put a little bit on this bit of pH paper. There it is. And you see you got a bit of a color change. Turns red. Don't know how good the color fidelity will be on the film, but this looks like, I'm just going to compare it by eyeball. Anytime you're comparing something by eye, be aware, people interpret colors a little differently. So it's crude. I'm going to call out a pH of about 2. So on my data sheet, I'll just put a 2 here. Then I'll take the next solution, which is orange juice. Put a little bit of that on my pH paper. That one looks like didn't change much. I'm going to call that about a pH of about 5, a little acidic. So I got a pH of 5 for the orange juice. Then I'll pull another sample out. Another bit of paper, get some milk. Milk kind of turned everything white, but ooh, wow. I'm going to call it 7. pH of about 7 for the milk. Then I'll get another bit of paper. Hit it with the soft drink. I think the ginger ale here, see what we get for that. Oh, a little reddish, orange. I'm going to call out a pH of 3. Put that 3 here. Now, the next one. Number 5 is 0.1 molar hydrochloric acid, which is going to be acidic. Whoa, that's very bright. I'm going to call out a pH of 1. And the last one, 0.1 molar sodium hydroxide. Whoa, look at that. That is very blue. I'm going to call it 12. Sodium hydroxide is the main ingredient in drain cleaner, which has a very high pH. All right. Then we'll do the litmus paper. So I have to use 2 bits. I'll go in the same order. I'll take vinegar, put a little bit on the blue litmus paper, a little bit on the red litmus paper, and they are both red. So all I can say for the blue litmus, it turned red. Red litmus, it stayed red. Next one. We'll do the orange juice, blue litmus, red litmus, red and red. So for orange juice, we went red, for blue, and the red stayed red. Next one. Milk. Blue. Still mostly blue. Red. Red with a hint of blue. They stayed pretty much, they didn't change that drastically. All right. So I'm going to say the blue stayed blue and the red stayed red. Now we'll go with the soft drink. Whoops, here's one red, one blue. Alrighty, soft drink. Blue litmus paper. Red litmus paper. Red is definitely red. Blue, it's reddish where the soft drink is. So we'll go red and red. And now we'll have the 0.1 molar hydrochloric acid on the blue, on the red, and they are definitely red for sure on the blue, red on the red. So the blue turned red, the red stayed red, and last one. We'll look at the 0.1 molar sodium hydroxide. Ooh, red turned blue, blue stayed blue, which is what you'd expect. So blue and blue for sure. Then the last thing, is it an acid? Is it a base? Or is it neutral? I guess I'll leave that for you to fill in, but it's, pretty obvious. If you look over here and you look over here, just all you're gonna tell me here is it's an acid, or it's a base, or it's neutral. So that one of those three words goes in these blanks. That's it. Now, what we'll do with the next one, I'll plop another video of procedure 2. Procedure 2 is kind of cool. What we're gonna do is use various pH indicators. You probably use this if you had an aquarium. You take a sample of water, just like we did for the freshwater ecology lab. You put an indicator in it. Most of these indicator dyes, they have a range of pHs where they will change color. We'll look at your data sheet. Should have right here. This lists the indicator solution. We'll use methyl violet, thymol blue, methyl orange, bromphenol blue, or Brahms cresol green. For these 1, 2, 3, 4, 5 indicators, this double arrow shows you the range it will change color. Here's the color it will change into. So what that means is methyl violet will be yellow until you reach a pH, a little above 0. Then it will change to violet if you have a pH of 2 or above. Between a pH of 0 and a pH of 2, you might get some intermediate colors in between the yellow and the violet. Thymol blue, notice the range is shifted a bit. Thymol blue will change from a pH of 1 to a pH of close to 4. It'll start off at red at the acid range of this arrow. It'll be yellow above a pH of, say, 3 or 4. It may have a transitional color between. Same with methyl orange. It's way up here. It's shifted to the right more. So below a pH of 4, methyl orange will be red. Above a pH of about 5, it's going to be yellow. Between the ends of that arrow, it might have a transitional color. Bromphenol blue, very similar. It's going to be yellow below a pH of 5. It'll be blue above 5, or sorry, it'll be yellow below, 4, and it'll be blue above 5. Between the ends of the arrow, it might have transitional color. And the last one, Brahms Cresol green, it's sensitive between about 4 and 6. So the pH, again, below about 4, it'll be yellow. Above 6, it'll be blue. Between those 2 points, it might have some sort of transitional color. So what I'm going to do is take an unknown solution, and I'm going to use these pH indicators, and that should allow me to narrow in on approximately where the pH is. That's what you'll be doing. I'm going to give you the color I get for these. We'll fill out the initial color is not very critical, but I'll fill out the final color, and then you'll just have to, from that color, pick out the pH range for each dye, and it should allow you to narrow down within a pH unit, so it's not that close. But if the pH is 2, you should be around 1 or 2 or 3. You'll get that close, and you'll be able to determine, this is what you'll be answering, kind of the final pH of the unknown solution. I may give you the first pH range for one of these, and then let's let you fill out the others based on the color in that previous chart. That'll be procedure 2. And then the last one we'll do is a little more complicated and much more accurate. Procedure 3 will be a titration. That allows us to calculate the molar concentration of an unknown solution. And it's really pretty accurate. It's a good technique to use. I'll show you how it works. A lot of our automated machinery uses titrations to figure out concentrations of unknowns. So I'll add this to the video next. Take care. Alrighty. What we're going to do now is procedure 2. It's determining the pH of an unknown solution using an acid-base indicator. All right, I've got 5 test tubes, numbered 1, 2, 3, 4, and 5. I'm going to add about 20 drops of an unknown solution. Here's my unknown solution. I don't know its pH. I will use this pipette to add 1 milliliter into tube 1, 1 milliliter, tube 2, 1 milliliter, tube 3. See, there's graduations on my pipette. 1 milliliter, tube 4, 1 milliliter, tube 5. All right, now, what we'll do next, I'm going to take a pH indicator. For tube 1, I'm going to use this methyl violet, which is kind of a, as you might guess, a violet color. Before I add it to my unknown solution, I've got thymol blue, methyl orange, bromphenol blue, and Brahms Cresol green. As I mentioned earlier, these all have a different range where they're sensitive to pH changes. So, I will take my tube number 1, so I'm working down here on the data sheet. This is procedure 2, determining pH of an unknown solution by using acid-base indicators. My tube 1 is methyl violet, so I will take a couple drops of methyl violet, 1, 2, add it to my solution. Mix it up a little bit. Now let's look back at that color chart. Here it is. Methyl violet. It's going to be yellow at a very acidic pH, say below 1. It's going to be violet from a pH of 2 up to 7. So look at that. That's definitely violet. So what we'll do on my data sheet here, final color, violet. So what's the pH range? Well, if I go back and look at that, all I can tell is the pH is greater than 2. So the pH right now I know isn't 1, isn't 0, but it could be 3, 4, 5, 6, 7, and so on. I know it's above 2. That's all I know. So that's it for the methyl violet. Then we do the same thing, tube number 2. We'll put in thymol blue. It's kind of a brownish color to start. 1, 2 drops of thymol blue. We'll look here at the color standard. Red to yellow. I'm going to call that yellow. It's not a red. So that means it's greater than 3. About all I can say there is the pH is greater than 3. So I'll go to my data sheet. And I'm going to say this is yellow. Greater than 3. All right, I'll go to methyl orange next. Methyl orange. And 1, 2. All right, there's my methyl orange added to my unknown. Let's see, methyl orange. Below 4, it's going to be yellow. Oh, sorry. Reading the wrong one. Below 4, it's going to be red. And 5 and 6, it's going to be yellow. I'm going to call that about yellow for the moment. That would make it greater than, for yellow, greater than 5. Oops. Greater than 5. Went to the wrong line there. Tube 4, bromphenol blue. Add it to my unknown. Oh, this dropper's pretty bad. That's kind of pretty. Yellow if it's below 4. Blue if it's around 5 or 6, above 5. So I'm going to call that blue. Which means greater than 5. Then we'll try the last one, tube number 5. Brahms Cresol green. Yellow to blue, that's definitely not yellow, it's blue. And that puts it let's grade those. About 6 or 7. All right, so those are my pHs with the various pH indicators. I know violet is greater than 2, thymol blue is greater than 3, methyl orange is greater than 5, bromphenol blue is greater than 5, Brom Cresol green looks like it was better than 6.5. It's about in the middle. So what you have to do, this is the part you'll have to answer, it's not very difficult. What should be the pH of this solution? Now, if you look at our scale, we're only looking at the acidic end. So all these unknown solutions have to have a pH between 0 and 7. Given this data, what's the best guess? Again, you might not be spot on, but you should be within a pH unit or 2. So I'll let you fill that out. I'll post this bit online. Let me go to the next procedure. Procedure 3 and 4, we're kind of together. We'll do procedure 3 first. I'm going to pause for a minute. All right, what we're going to look at now is procedure 3. This is basically determining the hydrogen ion concentration in an acid. Now what we're going to use is this device right here. This is a burette. It's just a fairly accurate way to measure volumes. This thing is filled with 0.2 molar sodium hydroxide. So I know what's in here, I know its concentration. Now in titration, what's going to happen is I'm going to add this base to some unknown acid. I'm going to mix up a concentration of this unknown hydrochloric acid. If I add sodium hydroxide, which has a lot of hydroxide ions in it, the hydroxide ions will neutralize the acid, and I'm going to put in a color indicator that will tell me exactly when I reach a pH of 7. There will be a color change in the solution. When I hit that pH of 7, I know how much sodium hydroxide I added to get to that point, and I can calculate exactly how many hydrogen ions then were in this unknown acid. So this is a really accurate procedure compared to all of the others. So let me zoom this down here a little lower, and I'll see if I can get us going. I'll kind of talk you through it a bit. So the first thing I'm going to do, I'm going to take 100 milliliters. This is just distilled water. I'm going to pour it into this Erlenmeyer flask because I'm going to dilute the acid. Then I take this unknown acid and I'm going to measure out 25 milliliters using this graduated cylinder, which gives you a fairly accurate volume. $25 of the unknown acid. Add it to 100 milliliters of distilled water. Give it a moment to mix. All right, then I'm going to cut this solution in half. We're going to use half of it for another procedure. So half of 125 should be 62.5 ml. So I'll use the graduated cylinder to get 62.5, as close to it as I can. Very close. All right, so this has 12.5 milliliters of that original acid. So there's 12.5 milliliters of that original acid in here. I'm going to pour that into this beaker. Set that aside. Now this solution here, this is another color indicator. This is phenolphthalein. You'll notice it's nearly transparent, slight yellow color to it. What this will do is when the pH goes from acidic, below 7, when it hits 7, this stuff will turn a fluorescent sort of pinkish color, very obvious. So I'll put this in. The instructions call for 5 drops. 1, 2, 3, 4, 5. Now you'll notice, put some paper on it, this beaker is clear. Just looks like water. What I'm going to do is add some sodium hydroxide, and right now my burette is sitting at 6.6. All right, get back to my data sheet. This is a data sheet I'll be posting. So milliliters of original hydrochloric acid. The unknown acid, there's actually 12.5 milliliters of that unknown original acid in this beaker. Milliliters of base, I don't know. Molarity of the unknown acid, I don't know. Molarity of base, that's a given in the instructions. It's 0.2 molar. It's also written on the burette. All right. Now what I'll do is I will take this burette and I will open it a bit and I will let the base, oops, see, get a little paper under it. little flashes of purple as that sodium hydroxide hits. See the kind of fluorescent purple in the turn? Now you gotta do this pretty slow because you reach a point where one drop goes in, it stays purple, and you don't want to overshoot. So I'll use a pretty slow drop rate. Swirl it a bit to keep it mixed. It's still clear. Slow it down a little bit because it's taking it longer to clear up. Start to take pink longer. Won't take much more. Another drop, maybe two. Oh, see, it's staying pink now. And it's just barely pink. And it's cleared up. One more drop. I bet it'll do it. That's about there. I'll put another drop in so it looks a little more obvious. And it's probably going to stay. That has now been neutralized. The pH is right about at 7. Now, how much of this did I drop? I am at 6 milliliters. So I added milliliters of base. I added 5.4 milliliters of base. So what's happening here? You're basically taking the hydrochloric acid in an unknown solution. You're adding sodium hydroxide. The hydroxide ions will neutralize the hydrogen ions. Basically, they'll combine and turn into water, and you're left with sodium chloride, which is the salt. I don't know how many hydrogen ions were in that unknown, but I know the concentration of hydroxide ions in this solution in the burette, and I know how much I added, 5.4 milliliters. So I'm going to plug it into an equation, and what I'm trying to find is this right here. This is what you'll have to find. The molarity of the unknown hydrochloric acid solution. So the equation is down here. You'll plug these numbers into this equation. It says use this formula to solve for the molarity of the unknown acid. Milliliters of acid, that's 12.5. Molarity of acid, that's your unknown. That's what you're solving for. That's X. Equals milliliters of base, 5.4, molarity of the base, 0.2. So you have this number, 5.4, this number, 0.2. You got this number, 12.5. You're trying to find that. And that is what will go in this spot here. In addition, that's not the pH, that's a hydrogen ion concentration. If you take that number and you take its negative logarithm, that'll actually give you the pH value on that scale of 0 to 14. So you can put in both the molarity of the unknown acid, so the molar concentration of hydrogen ions, take its negative logarithm, and that'll give you the pH. Put those both up here. Now, what is the pH of the half neutralized solution? This is for procedure 4. So we're using this acid has now been neutralized. It's got a pH of 7. There's no acid in here. This is neutralized. The other half I saved from before, this is not neutralized. So if I take these and combine them, This is what they're calling a half neutralized solution. Now, what I'm going to do for this is I'll get some pH paper. And I'll measure its pH approximately with this. And that looks like it's got a pH of about, I'm going to call it 2. So the pH of the half neutralized solution is 2. Now we go down to procedure 4. See, they're kind of linked. Procedure 4, that half neutralized solution, that's supposed to act like a buffer. Now there are a few issues with the way this experiment's set up. I don't know if this is actually a buffer, but that's what we're going to call it. So the starting pH is 2. Then I'm going to get just some plain distilled water. I'll go back to the sink and grab some. pH of the plain distilled water should be about 7. If our still's working right, I got about 6, so I'll write it down as a pH of 6. Now I have to run and get a couple small beakers, but what I'm going to do is take some distilled water in this buffer, and I'm going to see how they respond when I add acids or bases, see how much the pH changes. Let me run and get a couple small beakers to put them into. Be right back. All right. So now I've got 25 milliliters of my buffer solution, that half neutralized acid, in this beaker, 25 milliliters of distilled water in this one. Now, what my instructions are going to have me do is buffer solution. Okay, I'm going to add 5 drops of hydrochloric acid. There's the buffer. Hydrochloric acid, so we've got a pH of 2, and I'm going to add 5 drops of this acid. 1, 2, 3, 4, 5. Mix it around a bit. Measure its pH. And I could call it a pH of 1. It's fairly acidic. Now I'm going to take some sodium hydroxide. I'm getting another 25 milliliters of the buffer. And I'll add 5 drops of sodium hydroxide. 1, 2, 3, 4, 5. And maybe a pH of 2. It's hard to tell. Those colors are pretty close for my old eyes. All right, that's a buffer. Now we got the distilled water. This has nothing in it but water. We measured its pH. pH was about 6. Now I'll add 1, 2, 3, 4, 5 drops of hydrochloric acid. Measure the pH. And it's looking like a pH of 4. I'll measure out another 25 mLs. And add some sodium hydroxide. 1, 2, 3, 4, 5. Roll it around a bit. Whoa. Oh, it's hard to tell here. Eight or 9. I'm going to give it 8. All right. So I'll post these data tables on Blackboard in a Word format so you can copy them out. But basically, all you have to do with this data, you can use this data to explain the properties of a buffer, explain your results. So just so you know, a couple of sentences, just look up, what buffers are supposed to do in your ebook. That'll tell you what they're supposed to do. Did they do it and why? And that's all you have to do. So I'll get this data posted up, put the data tables up, and put the worksheet up. And all you'll have to do is basically answer a few of these questions. And that's about it. Take care.